student. In this video I am going to discuss about composite transformation. But before going to the actual topic, first going to this slide about concatenation of transformation. Concatenation means we know that if we add something in a consequence manner. Here you can see in the first line, concatenating. Affine transformations by multiplying together. We can find or we can apply that type of transformation. So suppose there are sequences of basic transformations. Basic transformations means, suppose if you want to translate or if you want to rotate or if you want to scale some objects, those can be called as basic transformation of any object. So if we are going to apply that type of transformation sequentially in the same object, then first define an arbitrary transformation directly. So any arbitrary transformation of those basic transformation, try to define it first directly. Suppose example here, there are three successive transformations. One, the object will go to P1, then P1 object will be transformed to P2 using B transformation, and P2 from P2 object from P2 point will go to Q point, applying C transformation. So here three transformations are there, A, B, C, and original location of that object is P, and in that way it will send to Q. So that is the concatenation of transformation. So here you can see, suppose we will achieve P1 if we multiply A with P1. A is one matrix, or you can say transformation factor, that will be multiplied with P1, as we have done in the homogeneous concept, that how we can multiply two matrices, one that is the location of the, or you can say position of the original points of the object, then multiply with the transformation factor. It might be scaling, it might be rotation, it might be translation, and we can multiply them using the transformation factor matrix as suited with your transformation. So P1 will be derived using A multiply P, then P2 will be derived by B multiplying with P1, and again Q, the final one, can be found by multiplying C into P2. Again in the Q we can replace C with this one, BP1, and P1 can be replaced with AP. So here you can see the whole Q, the final transformation can be obtained by C into B into A into P. CBA is the concatenated transformation, but in that manner, C then B then A, those are transformation factor. And at last we can say that Q equal to MP. This whole CBA can be said as one transformation factor if we multiply all these three and create a single matrix M. So applying the CBA, it will create M, and if we apply M on P, we will get Q. So this is all about concatenation, and that this concept is completely applied upon when we apply composite transformation. Let's see what is composite transformation. But we know that if we apply the concatenation properties, suppose there is three transformation, we can multiply M2 or M3 first, then we multiply M1, or we can multiply M1 and M2 first, then we multiply with M3, because all these three should be same dimension. In that case only you can do that. So suppose here you can see this one house is translated to this position first, then this is rotated that is the final position. Or you might say this object is rotated first, then this will be, and then translated. This will be the final position. Okay, so order of, but here you can see transformation is not commutative. Transformation is not commutative. Here what you cannot do is that you cannot place M3 before M2 or M2 after M3 or M1 between M2 and M3. Here you can see two differences. Here if we apply first translation then rotation, the object goes to that location. But if we apply rotation first, then if we apply translation, that object goes to that final position. So here you can see these locations are different, but the multiplication is associative. You can multiply in the matrix part M1 into M2 first, or M2 into M3 first, then M with M1 or then with M3. But the transformation is not commutative. The order of the transformation may affect the whole transformation position. That is why you need to take care about that property. So next we are going to talk about the main concept, that is composite transformation. So in this concept also that point comes like a sequence of transformation will occur. Calculate the main composite transformation matrix rather than applying individual transformation. So suppose P dash is your final location of the object. By applying M2 and M1 sequence transformation on P, then M2 and M1 try to multiply it up to create the main transformation matrix rather than you apply individual transformation. So composite two-dimensional translation, it might be like this. Apply two successive translations, suppose T1 and T2. Suppose T1, the factors are like T1x and T1y, and then T2 factor or translation factor 2, that is T2x, T2y. Means those are translation factor, different translation factor, and that are going to be applied in successive manner. Then we can create, suppose here you can see P dash can be obtained by multiplying the P with T1 first, then whatever we get the result again we apply with T2. But you can also do that, that is what it is saying, that rather applying individual transformation, try to find the composite transformation matrix first. We can do what? T2 and T1 try to make it one transformation matrix rather than applying it one by one. You can do also that, but you might create mistake if there are 4, 5, 6 number of transformation matrix are there, and if you misplace the position of the transformation factor, then it will end up wrong. So before going to apply the thing on the original object, you try to create the main transformation matrix first. So T2 and T1 multiply first. So composition matrix transformation in coordinate form will be like this one. If we multiply the translation matrix T2x, T2y into T1x, T1y, it will become like this if you follow the matrix multiplication rule as per the homogeneous coordinate system. Here you can see composite two-dimensional rotation. Suppose you want to apply two-dimensional rotations successively, suppose R1 and R2 into a point P. Suppose P dash, you are first apply theta 2, then again you are going to apply theta 1 rotation. So rather than applying individually, you can first create the rotation matrix or rotation factor matrix, multiply two rotation matrices to get composite transformation matrix like this one. So here r theta 1 and r theta 2 will be equal to r theta 1 plus r theta 2. If we go through the matrix multiplication and trigonometric equation rules as per the homogeneous matrix format, you will get that type of conclusion. So that is why try to go through the previous videos also and try to apply that to understand how we can get theta 1 plus theta 2. So after getting the theta 1 plus theta 2, we can apply the whole rotation matrix with the original object to get the final object. Again, same way we can apply it on scaling. Here you can see as S1x, S1y, S2x, S2y, two different scaling matrices. Here, if we apply them, or if we can multiply them, and it will become like this. S1x will multiply with S2x, and S1y will multiply with S2y. Then this whole scaling matrix will multiply with the original object, and we will get the final object. So suppose you need to apply two-dimensional pivot point rotation. Pivot point means a point about which the object will rotate, but that point is not the origin. So that is why it termed as pivot point. So pivot point is not origin, it is a different point. It might be inside the object, it might be outside the object. So graphics package provide only origin rotation. See here, in general, whatever object you put in your screen or in the display screen, or whatever transformation you want to make, in that rotation or the graphics package works with reference with origin only, not with any other points on the screen. The graphics packages will follow the origin rotation. So that is why you need to perform some evaluation matrix, or you need to perform some calculation, so that like the concatenation, like the matrix composition, so that you can use that graphics package as your desired way. Here you can see, suppose you want to perform a translate, rotate, translate sequence. It means first you will translate an object, then you will rotate that object, then again you will translate that object, and in a sequence. So first what you will do, but whole situation will be act on a pivot point. So translate the object to move pivot point position to origin, then rotate the object, then again translate the object back to original position. So this will be the composite matrix in coordinates form. So here you can see TXR, YR, that is translation matrix or translation factor, that is applied here. The first point, translate the object to move pivot point position to origin. So what you try to do, if you want to rotate an object and translate an object, then you need to first, here you can see what it is actually doing. Actually doing is like, actually the object is rotated with respect to a pivot point. So what is our procedure? Procedure is that you need to move that object from that pivot point to the position of origin. Means we are going to translate to the origin first, then we will rotate the object with respect to origin, and then again we will translate the object back to original position by reversing that translation factor which we have applied first. So ultimately the whole object will be rotated as per your pivot point, but that is why it created in that way. First we translated to the origin, then we apply a rotation with the origin, Then again we translate the object from the origin. Suppose here you can see in this point, in this picture, first the object, the triangle, original position was this, and the pivot point was this one, XR, YR, and your work is to do rotation with respect to that point, not with respect to origin. So what you will do, you will first translate the object so that pivot point XR, YR is at origin. So this point reference will be translated to this point first, so that the pivot point XYR YR is at origin. Then you will apply the rotation about the origin. Okay, you will rotate about the origin. Then again you will translate this object to that point. Translation of the object so that the pivot point is returned to position XR YR. So to do a rotation with respect to a pivot point, we apply this composite transformation process. Okay, that is why this is important, because in general graphics packages does not provide you rotation with respect to pivot point. It provides you only rotation with respect to the origin. So to use that package, you can do this composite transformation process to achieve that transformation. Here you can see again same part from this previous, how the equation changes. So first here you can see Txr yr r theta and T minus xr minus yr, that is the reversing of the or reverse translation. So ultimately the main transformation matrix is this one. So how can we get that? Here the first translation matrix, because translation matrix, in case of translation factor, the value will be here, but in case of rotation the value will be here in the matrices, and again the reverse is here. And to make it homogeneous, we are applying this one value here to make it three-dimensional, and all the dimension of these three matrices are same. And after you apply the multiplication, you will get this equation. You will get this equation. So ultimately you are going to apply this matrix with the original object point to find out the transformation. So this matrix is the composite version of the original 3 matrix, and original 3 matrix is created because we need to rotate the object with respect to pivot point. So same type of thing can be applied in case of you want to scale an object with respect to a fixed point. Then we need to first translate the object to move fixed point position to origin, then scale the object with respect to coordinate origin, and again use the inverse translation in step 1 to return the object back to original position. Same process if you want to scale an object with respect to a fixed point, or you can say pivot point. Here first you are going to apply the translation so that the object goes to origin position. Then again you apply scaling with respect to origin. Then again you return back your object to the fixed point location by applying the translation factor in reverse way, and ultimately your whole transformation can be converted to a single matrix, that will be this one. So how can we get this? We can see here So initially this is your object, okay, with respect to a pivot point. Then first you will try to translate that object to the origin, then you try to scale that object, okay, you try to translate, then scale, then again you try to translate it back to fixed point or return it back to the fixed point. So that is the process. Now we are going to see how it happens in the matrix formation. Here you can see first translate. So in the translation it will go to this equation, then it will scale, then again translate. So ultimately it will become like this. Here you can see translate with this factor, then scale with this factor with respect to origin, then again reverse back with this scaling factor, that is sx sy, and this matrix will be formed. And here you can see that as xf and yf nothing but the distance between this point. So this distance is this factor, okay. So that in that way we can achieve this composite transformation matrix to rotate the object with respect to a fixed point. So again, if we want to suppose general two-dimensional scaling directions, perform a rotate scaling rotate sequence. Suppose you need to perform a rotate scaling rotate sequence, then composite matrix in coordinates form will be like this one. First you will rotate first in an inverse direction, you will apply the scaling, then again you revert back the degree. So in that way it will become like this. So suppose this is the way to compose or concatenate, we can say now, concatenate any transformation, sequential transformation. Here sequence is this one, rotate, scaling, rotate. So if we apply in that multiplication form like the previous ones, you can find this one also. So here you can see initially that whole reference x-axis system is rotated by that theta, okay. Here you can see general scaling direction is, so this whole reference actually, like here this theta is going to rotate back, that is negative direction, to this location, and again apply the scaling, again return back to the location. So if we apply the same thing on this, suppose you are going to apply this whole sequence on this object, so you have to apply this whole matrix on that object, and thus you will get this parallelogram. So this square is compared to parallelogram because you just scaled and with a rotation, scale with a rotation. So that is a composite transformation, okay. So that is all about in this video. Try to do this math actually, it is very important. Try to apply the thing, that how can we achieve these values 1 by 2, 3 by 2, 2, 2 and 3 by 2, 1 by 2 if we follow this composite transformation process. That is your homework. Try to find it out.